Let's Make It is brought to you by Ting, the new way everyone is getting their cell service. No overage penalties, great rates, keep what you do not use, no contracts, and someone will actually pick up the phone when you need support. Use our link and get $25 off your first month's service or your new phone. Just go to tech-zen.tv/ting to save $25. Hello, it is 9 p.m. Eastern Time on Monday, and it is time for another Let's Make It. This is episode 35, recorded on September 9th, 2013. And this week I have a special guest. I have John Hall. How you doing, John?
Hey, Mike.
So John is from NXP Semiconductors, and he's come tonight to talk about I2C with us. But before we get to that, let's do a couple of little things here first. So I got an email this week because Halloween's coming up, and actually I don't dress up for Halloween. I don't go out and do anything for Halloween. Do you enjoy Halloween, John?
No, not at all.
Okay. Well, we had a request about doing some episodes on like how to make, I guess, like things move for Halloween, like make a ghost pop up or things like that. So we're going to start thinking about this out a little bit. Maybe as far as like having Arduino control spooky sounds or some kind of lights or something like that. So if you have ideas, send us the idea and we'll maybe try to put that into a show before Halloween. So maybe you can scare your neighbors or your neighbors' kids a little bit. Just real quick, you can watch us on YouTube at youtube.com/TechZenTV. And you can also get all of our show notes at TechZenTV. Or you can go to letsmakeit.tv, and it's a shortcut right into the right page in TechZen. And if you follow us on Twitter, make sure you use the hashtag Let's Make It if you tweet about anything on the show. We do watch that hashtag, and we'll respond if we see that. All right, one last thing, one more marketing thing. Facebook.com/TechZenTV. Please go out there and do the like. We're trying to get our likes increased a little bit out there. All right, so this week we have John, and he is an I2C expert. And we've been using a lot of I2C, and actually I've been mentioning the switcher I've been building. I'm actually using it this week to do the switching. So it's here in front of me, and I'm using everything as I2C. Every 8-button board is I2C. It's actually one of the chips that John's company sells that controls the LEDs. I remember the 9635, is that the model number?
That's right.
So I'm actually controlling the red, green on the switcher and the different colors, all using that chip. And then the 23017 for what buttons I'm being pressed. So this whole thing is I2C, and I have 5 different boards right now mounted on here that are all controlled via I2C. So this is a very timely topic for me, and I have some questions for John. I kind of gave him a little bit of a heads up already for that one. So John, are you ready to take over and start?
Absolutely. First of all, I'd like to say thank you very much for using I²C. That's keeps me employed. So let me switch over and share my screen, and we'll get started on a presentation that I've done for Let's Make It for this week on I²C. Okay, this is the title page. Can you see that, Mike?
Yep, I sure do.
Okay, very good. So my name is John Hull. I'm Technical Marketing Manager for I²C products at NXP Semiconductor. We are going to talk about I²C, which stands for Integrated Circuit Bus. Now, one of the things that you may not know is that it was invented by Philips Semiconductor, which is now NXP, over 30 years ago. It was devised as a simple, low-cost way to communicate between ICs in a television set. And of course, back then, Philips was big in television sets. So it was a very timely development. Over those 30 years, the specification has evolved. There's probably 5 or 6 different specifications or versions of the specifications. it started out as a 100 kilohertz standard mode, and that is what the Arduino wire library defaults to. From there, it went to 400 kilohertz to increase the bandwidth, up to 1 megahertz, which is called Fast Mode Plus. Also included in the specification is a 3.4 megahertz high-speed mode, and that was really designed for smartphone sort of applications, moving a lot of information to an LCD display over a relatively short period of time. And there's also a 5 megahertz ultra-fast mode, which is unidirectional, and that is very, very direct for gaming applications. Philips licensed the I²C specification, a lot of the hardware things, for many years, and that caused many variations. So there is something that is almost identical, and you can see that in the Arduino, the two-wire interface. The reason they called it two-wire interface is to try and skirt some of the legal situations. But there are a large number of different devices that are pretty much exactly the same as I²C, and that's SM-Bus. You'll see PM-Bus for Power Management Bus, IPMI, and ATCA, which is in the telecom world. And actually, even HDMI uses I²C to set up the communications between the different devices.
Yeah, is that what they consider the HDCP protocol? Is that part of I²C?
Yes.
See, I never knew that. I learned that. That's interesting.
So where is the I²C bus used? I mean, really everywhere. It's pretty well hidden, but it is a very widely used protocol. In cell phones, all of the sensors, the accelerometers, the gyroscopes, temperature sensors, they almost exclusively use the I²C. The other place where the other ICs that you see that use a lot of I²C is EEPROMs. And the reason for that is to keep the pin count down. And these EEPROMs are used for initialization and configuration data storage. So it's that you don't need to access it all the time. You only really need it at power on. And these EEPROMs are used in the DDR4, DDR3 memory DIMMs, and that stores the what the configuration of the DIMM is, what the speed is, so on. Another place that I²C is used a lot is in digital potentiometers, and that's for remote adjustment of analog circuits. And the other place that you'll see I²C a lot is in LED drivers. So even though it is hidden, there is a large number of devices being used. Now what we're going to talk about today is, first of all, I'm going to be talking mainly about the hardware. And what I'd really like to talk about is some of the infrastructure of an I²C bus system. And what I mean by infrastructure is not necessarily the sensors, the gyroscopes, all of those sort of things, but really the things that you put together to make a system work, an I²C system work. So the first acronym that you'll see is GPIO, for General Purpose Input Output. And this is particularly good when you run out of I/O pins. And the advantage there is you have two wires, two I²C wires, that go into the chip, and 8 or 16 inputs or outputs coming out. So this allows you to put the IC where you really need the inputs or outputs, and not route a whole bunch of wires. And this is particularly good for enunciators, for such as switches and LEDs. So somewhat similar to what Mike is doing in his switcher. And then there's various output configurations to drive custom loads. Another thing that is a major part of the infrastructure is something called a MUX or a switch. And what that does is takes one I²C bus and multiplexes that bus onto 2, 4, or 8 different I²C buses. And what that means is that you have, if you have an address conflict, if you have a GPIO, for example, that has the same address as another GPIO, you can use the MUX in between the master and isolate those bus segments. So the MUX, as I say, is one downstream bus. You have one upstream bus, which is the master, and a MUX has one downstream bus. A switch will allow you to connect any or all of the downstream buses to the master.
So how does the master determine which one it wants to talk to?
We'll get into that a little bit further, but okay. Basically there's an address, a different address for the MUX, and it's a simple register write which sets the downstream buses to connect.
Oh, okay.
The other piece that a lot of times is useful is a bus controller. Almost all of the microcontrollers nowadays have an I²C peripheral, but for one reason or another, you may or may not want to use that I²C peripheral. So the bus controller is a parallel interface to a CPU or some other micro as an input, and the output then is multiple streams of I²C, a very easy interface. And the software is relatively easy, or at least much easier than trying to program some of the more complex micro peripherals. And then lastly, bus buffers. The buffer allows you to drive long lines or heavy capacitive loads. If you remember, the I²C bus is open collector. It's very analog intensive. So being able to amplify the signal helps in a lot of cases. In other places where a bus buffer is real useful is in level shifting, especially when you have two different systems at two different power supplies. The buffer then allows different I²C voltage level on both the input side and the output side. So I guess before I get too far, we should go into some of the I²C terminology. The master is the device that really controls the bus. It's typically the Arduino Atmel Micro or something similar. And as a general rule, it's the only device that supplies the clock signal. The slave is typically a peripheral device, and typically it reads the I²C address and the register address, and then typically writes sensor data back to the master. So one of the nice things about the I²C is it is a bidirectional bus. It allows both reads and writes. And we'll get into that a little bit later. The I²C address is a hardwired address that each slave reacts to. It's limited to 127 different devices, and there are some reserved addresses. One of the problems is that, number one, there is only 127 different addresses. And in a large system, that may be kind of limiting. The other thing is that there is static enumeration. So typically, you need to hardwire each slave to a specific address rather than automatically assigning. Now, there is some relief to this, and that is a 10-bit address mode. But again, a lot of times that isn't really implemented, so you have to beware there. And again, with some hardware workarounds, it is pretty easy to get around this limitation of 127 or an 8-bit addressing mode. The other thing is that the outputs, or the bus itself, is based on open drain outputs, which means that there's an active pull down to ground, and you need a pull-up resistor to VCC. This is that can cause a lot of analog problems because it depends a lot on the capacitive loading of the bus, the speed that you're running at, to optimize the pull-up resistor. The advantage, however, is that any device on the bus can pull the bus low. So consequently, you end up with a wired OR configuration. And in the sort of best case or worst case, two slaves can have the same address and be connected to the bus at the same time. The slave that has the most zeros in the output is the one that will be read by the master. So there are a lot of advantages to this sort of funny analog bus. And the last thing is an acknowledge or a not acknowledge every packet. There is a handshake every 8 bits of data that sends that goes back to the master. And what that allows is that the master knows that the message it has sent out has been accepted. In SPI, for example, a lot of times the master can send out data and the message may not be received by anyone, and there's really no way for the master to know that. So what I'd like to do is to go through some tips and tricks, some ways of helping debug some of the problems that you usually run into in an I²C system. Really, the first one that is probably the number one issue, the one that I fall into, I think everyone falls into, is forgetting pull-up resistors. Without the pull-up, because the outputs are open drain, you absolutely need pull-up resistors to make the high level. And just as a rule of thumb, at the standard mode, or 100 kilohertz, probably 10 kilo ohm pull-up resistor on both the clock and the data line is good enough. It can be a little bit lower, but that's okay. At 400 kilohertz, or standard mode, a 5 kilo ohm pull-up is okay. And in the fast mode plus, a 1K typical pull-up is probably called for. Another thing to watch out for, besides forgetting them, is having too many pull-up resistors connected on the I²C. You can't have a pull-up for each and every slave. There's only a 3 milliamp pull-down capability of the I²C devices in the standard mode and the fast mode. So that means if the resistors get to be too low, you won't be able to make a low level. The other thing that people sometimes run into is being sure that the pull-ups are connected to the correct voltage. The I²C inputs and outputs are very flexible and robust, but there is 5-volt buses and 3.3-volt buses, and if the pull-ups are connected to the wrong voltage, you won't be able to meet the high level. There are a lot of ways of getting around this voltage level translation, and it's really a topic unto itself. It's a very analog intensive topic. So when you're doing debugging, I guess the thing is don't get too fancy right off the bat. Double check that the clock and data are correctly wired. In other words, I always switch clock and data, and then sort of scratch my head what's going on, and eventually I get back around to rechecking my work and seeing that I have those two lines switched. Very easy to do, and don't be ashamed of it. Double check it every time. So that cures a large number of problems, non-functioning I²C system problems. Another thing to take a look at is the address. So there's a couple of things. Each individual slave has a hardwired address, and as you can see in the timing diagram or waveform below, after the master sends out a start condition and an address byte, the slave must turn around and acknowledge that address. If the slave doesn't acknowledge the address, the entire transmission is aborted. So consequently, if you're looking at the I²C bus with a scope, this is the thing that you'll see. And you'll know that the system is not functioning because the slave has not acknowledged the address that the master has sent out. Now, one of the reasons for that may be simply a terminology problem. If you look at the address byte, there is typically 4 bits that are hardwired into the system. And in this particular case, it's the 4 high-order bits, 0100 or 4. And the lower 3 bytes are hardwired on through the slave pins, which I guess I should have put X's in instead of the 0. So that's B3, B2, B1, which allows you to put 8 of the same peripheral on the bus by simply varying the hardwired I²C address. So in this particular case, the address that we show here is a 40 in 8-bit format. There is another format that is a lot of development tool software uses that's called 7-bit format, which ignores the read-write bit on the far right-hand side and shifts everything 1 bit to the right. So in that configuration, or in that terminology, this I²C address is 20. And in 8-bit format, it's a 40. So be careful about the terminology being used, because this naming convention always causes problems. So as we were talking before, the real quickly, a very simple device would simply, as shown in the first bullet, would simply send out a start and a slave address and a read or a write. In this particular case, and then the next byte to send out would be register data. And all of these are acknowledged by the slave. So, Mike, in answer to your question, the muxes and switches would send out or the master would send out the address to the mux with a write, and then the register data, which is the actual, depending on how the implementation is, the actual data to turn on the individual downstream channels.
Gotcha. Okay. So before we go too far, I guess the other question I had is about the addressing. I have some chips that have like 5 address pins. Some of them have 3. Is the reason just to keep the pin count lower? Is that why they?
Yes.
Okay. Because I know on the chips that I'm using on this board, for example, one of them, I think yours does 5 or 6 pin addressing, and the other one does 3 pin addressing. So I wasn't quite sure.
A lot depends on the usage case. The LED drivers, you would imagine that there would be a large number of them on the bus.
Right.
Because you just normally, or in many cases, would drive a lot of LEDs. Consequently, the number of bits that you have would allow you to have many more drivers on the same bus. And then others, so GPIO or temperature sensors, normally you wouldn't expect to see that many on the bus. So 8 is gracious plenty.
Yeah, I guess the thing that's probably confusing to me is because the 23017, which isn't your chip, is the one I think that does 3, and it's a general GPIO, and in my case I have 16 buttons sometimes on a board, so I very quickly can run out of those. You know, it doesn't take very long to fill up, you know, the 7 chips or whatever. So I was just more curious what the thought behind it was a pin count reduction or what it was.
It's trade-off on usage model and available packages.
Gotcha. Okay.
So going back to the complex device, the second bullet, the protocol is that when you write, and this is a write only, when you write to a complex device, you write the start, you write the slave address, you write a pointer address, and then you write register data. So this is, for example, in a GPIO, or an LED driver would probably be a better example. There are a number of different registers, one for brightness, one for red, one for green, one for blue. And it would be impossible to do with a single 8-bit register. So there is a pointer register that then indirectly addresses the rest of the data registers.
Yeah, I know that your chip that I'm using has multiple registers in it. Because I have the one that does the PWM.
Exactly. I think it takes like a setup of 20 registers to actually get the first display. Now going to the read, what we have is a simple device. And again, this is very, very straightforward. One sets the start, the slave address, and then the read bit embedded in the slave address. Then it reads the register data and stops.
So how does it deal with collisions? Is there any possibility for collision, or because the master's controlling it all, there's no possibility for collision?
There really is no possibility for collision since the master controls the clock. And again, as I say, if 2 slaves are at the same I²C address, the one that sends out a 0 is the data that the master reads. So it may be incorrect data, but there is no real collision. Now there is the possibility to do multi-masters, but that is a very odd case. It's very The scenario doesn't occur very often, let's put it that way.
So if something would happen that the slave would die, it would basically know that because it wouldn't get the ACK for the slave address, correct?
Exactly.
Okay. And is there like a certain timeout period that it waits depending on the speed of the protocol, or?
The original I²C spec will run at 0 hertz. The SM-Bus enhancement to the spec will actually time out after 35 milliseconds.
Okay.
Most masters will, if there is no activity, if the master driver is well written, will look for activity and we'll do something. We'll do a timeout.
Okay.
So then real quickly, going back to the complex device, this is the read is somewhat difficult because the master must must write a address, a slave address, must write a register address, but then turn around and read the data that the slave sends it. So we won't go into that. We won't go into that protocol very much. But there is something called a restart that allows one to do that relatively easily. It just makes the waveform a little bit difficult.
So the data that the slave sends back, is it always like one bit in length, or can it be more than 1 bit in length? Or 1 byte in length?
So it's always 1 byte.
Always 1 byte, okay. All right. All right.
Because the acknowledge, each byte is acknowledged.
Gotcha, okay.
So there's the way to send more information is to not stop after, well, the acknowledge when the master is reading means that it has read the data and is ready for more data. Once it's read enough data, then it will not acknowledge back to the slave. Gotcha. And that terminates the read operation.
Okay.
So I'm taking way too much time here. Some advanced topics that we were talking about. This is the multiplexer that we were talking about before. On the left-hand side, an Arduino is a master. And on the right-hand side, 4 temperature sensors, all with the same address. So 90 hex. Normally, that would not be a very good, or it would be impossible to put all of those 4 temperature sensors on the same bus and get 4 different readings. There's just no way to access them. So the one way to do that is using a MUX, and the address of the MUX is E0. So it's different from the other downstream devices at 90. So the master would send out the MUX address, send a data byte to turn on one of the downstream buses, and then access the temperature sensor on that particular bus. The master, after getting that data, the master would then turn on the second bus and read that data. Turn on the third bus and read that data.
So I see. So basically it's basically extending the bus down one of 4 options.
Exactly.
Okay.
The other piece, or another advanced topic, which is very interesting, but sort of difficult to explain, is the bus buffer, I²C bus buffer. So if there are too many slaves on the bus, or you're working with long lines, that means that you have an increased amount of capacitance on the bus. And remember, we have pull-up resistors. We don't have active driving that bus capacitance. So the pull-up resistors and the bus capacitance determine the rise time. What can happen is that the rise time gets so long that it won't meet specification. Consequently, you need a bus buffer, an amplifier, to divide the bus into segments and isolate the capacitance on each segment.
So what's the distance you think is the max distance for something without a bus buffer before we start having problems?
It depends on what sort of wire you're using, how fast you're running. That's why I say it's an analog problem. It really depends on so many variables that you need to do the calculation for each and every one. You know, I do a lot of funky things in the lab, and I usually don't have a problem with wires that are 2 feet long.
Okay.
I start running into problems at like 3 feet.
Okay.
So 1 meter is probably a good lab number, but for production, it's probably less than a foot.
Okay.
The interesting thing about bus buffers is, remember, the I²C bus is bidirectional, and there is no direction pin. So it is a very challenging design to make a functioning bus buffer at the I²C higher speed modes work correctly. The other thing that a bus buffer is good for is they normally can allow or permit different voltage, power supply voltages on the, if you will, input and output side, or the A side and the B side. And this is good if you are running a 5-volt master and 3.3 volt slaves, for example. Nowadays, the master sides, the CPU sides, are going down to below 1 volt, and a lot of the slaves still run at 3.3 volts. So voltage level translation is kind of important. And the last thing that it's good for, a bus buffer is good for, is to protect your I²C master when the bus goes to an uncontrolled outside source. So, for example, HDMI implements a buffer because there is the great unknown is out there, and you connect an HDMI cable to your television set. You have no idea what it's going to plug into. So that protects your expensive television set. And that's really all I have. I hope I've given you an overview of I²C and some of the problems that you can run into, and maybe a couple of solutions that might help you debug your system.
Yeah, that was actually very, I learned a lot from that, so that was great. And I never even thought about a switch. I've often wondered how would I go more, I know I can do 7, with what I'm doing here, I can do up to 7 boards in particular. I always wonder what I would do if I needed to go beyond that, so that answers that question. Yep. And what's the biggest mux? You said it was 8?
8, yes.
Okay. Yeah, that's more than enough. That's what I'm trying to do. I just wonder if ever I wanted to go to like that 8th board, on this controller, what would I do at that point? So I need to start planning for that ultimately, I guess. Yep. That's very, very interesting. But I really appreciate your time and the effort you put into putting it together for us too. So NXP, you said, was a former Philips company, or was formerly Philips?
Yeah, Philips Semiconductor spun out its semiconductor operations approximately 6 years ago. Okay. So you make things other than I²C? Oh, absolutely. We have a huge portfolio of logic devices, transistors, micros. I've only worked here now for 2 years, and I know about a hundredth of the portfolio.
Right. So your specialty is in I2C.
Exactly.
Okay. Yeah, I never knew that was NXP was spun off from Philips. I didn't know that. So that's interesting. When you first contacted me, I thought maybe that was your specialty of the company was just I2C stuff.
Yeah.
Okay. I really appreciate you joining us. You want to hang around, or you need to go?
I really need to get going now.
All right. I appreciate it. All right. Well, thank you very much. And maybe we'll have you back in sometime in the future too. We have more questions.
Sounds great. Thanks for having me.
All right. Thanks a lot. All right. See ya.
Bye-bye.
Bye. All right. Special thanks to John. That was very, very interesting. So, actually, and Bob, if you are listening, I see you just got in. You can call in if you want for the second part of the show. Sorry, I just now saw that. So the second part of the show, I mentioned 2 weeks ago that we were going to do a rotary encoder and a stepper motor. So because that John was willing to spend his time with us, I decided just to do the stepper motor this week, and I'm going to show you what we're going to do next week with the stepper motor, because the stepper motor is going to take a little bit to explain. And I wanted to walk through a couple different projects or different sketches to kind of show how that worked. So what I want to do first of all, let's show you what a stepper or encoder is. So encoder, this is this round thing right here, and if you'll be able to hear it when I turn it, it clicks. You can kind of hear it maybe. So the thing is with a step or with a rotary encoder is it just keeps turning, it never stops. So if you're thinking potentiometer, a potentiometer actually has a beginning and an end. So you can only go so far left and you can only go so far right, and it works off of resistance. So when you're typically when you're full left, you are, oh, let me get Bob here real quick. You there, Bob? Oh, hold on. How are you there?
I'm here.
There you go.
I'm very late.
That's okay.
I'm very sorry.
That's okay. So, say hi, Bob.
Hello.
Okay, so what I was talking about there was the potentiometer is typically it starts and stops at a location. So you go full left and you're going to stop. If you go full right, you're going to stop. And normally if you go full left, potentiometer is at its lowest value or the least resistance, and when you go full right, it's at its highest resistance. But with a rotary encoder, it just turns forever. There's nothing to stop it. So it's not based off of resistance, because if it was, when you went the whole way around, it would go back and start over again. So the way a stepper works is, and most of them have 2 pins and a common, and as you turn it, they change combinations of what's high and what's low in a particular order. And because you know the order, you can tell which direction it's spinning. So what I've done is I've created, first of all, a sketch in the Arduino, and I'm going to turn the stepper motor, or I keep calling it stepper, the rotary encoder, and every time it rotates, you're going to see the pins change. And then I'm going to show you a sketch. I'm going to show you 2 sketches. One of them that will basically work half time, and then we're going to go in and look at both pins. So we're going to do 1 pin at a time. So the first thing I want to do is get over here to the Arduino code. And let's see. I'm actually going to bring this up on the screen. So you have the rotary encoder here, and you have on the left-hand side over here, let me do this. Let me change my screen resolution. I should know this before I get started. So you can actually see this. All right. So what you see right here is these zeros going up and down. And right now, both these pins are low. And I'll show you what the pins are in the sketch, because there's really only 2 pins being used on the Arduino. But as I rotate it once to the right, you see now it's 0 and 1. So basically the second pin is high. I rotate it one more time, and now both pins are high. And I rotate it one more time, and now the first pin is high, the second one is low, and I rotate it one more time, and they both go low. And if I keep going, you're going to see it goes to 1, and then to 1, 1, and to 1, 0, and then to 0, 0, and to 0, 1. So, and if I go backwards, it does the exact opposite order. So because it's predictable on what it's going to give you, we can write a program to figure out which direction it's spinning. So let's do this first. I'm going to stop this. I'm going to show you this source code. So this is basically the watch encoder. And it's very short. You notice there's no, I hardly put any comments in here because I want to show you how short this stuff is. So here we are defining our 2 pins. So I've defined pin A of the encoder to be 2 and the pin B to be pin 3. And the third pin on the encoder just goes to ground. And then I do that because I put these in input mode with pull-ups on them. So they should be 1s if I'm not going to ground. I'm starting up the serial port, and then you see I'm looping, and every 1/5 of a second, I'm outputting the status of the pins, encoder A and pin B. So what we were watching was me showing you what these 2 pins are. So if we look at this, let me go back over to the actual unit here, and you see we have 3 wires. We have ground, which is the center pin right here, going to ground, and then we have encode pin A and encode pin B. A is pin number 2 and B is pin number 3. So very simple 3-wire interface to read the encoder. Now, since we know what the encoder is doing, let me go and bring up a different sketch and load it here. And I'm going to show you how we can determine what direction it's going. Looking at the sketch. Off my screen whenever I did this adjustment. There it is. All right, let me load it. All right, it's been uploaded. Hang on a second, I got the wrong one. Let me open this back up again. Okay, it's uploaded. Let me do this. Let me go back in and do the serial monitor, and we're going to go back over to this view, and you see up here on the right is the encoder, and what you'll see on the screen is a -1. Then you see I'm turning to the right 1 step at a time. Okay, there it's 0, and then another step, another step, another step, and then another step. So there we go to 1. So you're seeing it's taking me 4 steps to go up 1. And I'm going to show you why that is, and then I'm going to show you how you get around this. So every time I click 4 times, it goes up 1. Just like that. So, and going the other direction, if I go back 4 times, it goes down 1. If I go back 4 more times, it goes down 1. You can hear me spinning and clicking it. So it's not very accurate at this rate. And what I'm going to do is I'm going to show you the code that we're running right now, and then I'm going to show you the code that you get around that with. So let's first of all look at basically the same code as before. You see I have the pins defined as 2 and 3. And then I have a couple additional variables because I need to keep track of where I'm at in the number scheme and what the last thing was that I read. So you see I'm reading input pull up pin A and B like before, same serial, starting it up. I read pin A, and if I say that encoder pin A last, which means last time I saw it was equal to low, but now it's high, then I need to look and see what pin B is, and based on what pin B is, determines what direction I'm spinning the knob. So the problem with this is that pin A only goes high, from low to high, once every 4 clicks. So it's only going to check this once every 4 clicks. So I also want to show you why this is. So let me go over here, and I'm going to show you, this is the encoder that I'm actually using, the Born encoder. And if you look right here, let me zoom in a little bit on this. Come back down. So if you look right here, you can see that we have our A and B channels, and see channel A is on top, channel B is on the bottom. So as you're rotating it clockwise, it goes, when A goes high, if you look at B and it's low, then you're going clockwise. And here goes A high again, and it checks and it's low, so you're going clockwise. Where if you look at A going high, so you're going counterclockwise, you're going to notice that it goes high when B is high, going counterclockwise. So by comparing the two states of these, you can determine which direction you're turning. So if we go back over and we look at the actual source code, and let me make this a little bit bigger so we can see it. You can, let's see, let's get back over to this view. You can see that we're only comparing pin A when it transitions from low to high. So what we need to do is we need to look at every transition of both A and B. So what I'm going to do is I'm going to open up the other one, which I have here, which is the second program that I wrote. And again, very simple. At the top, you're going to see everything's still the same. But you see I've added this encoder pin B last, so I can keep track of that. Doing our input pull-ups right here. Let me bring this up a little bit bigger. All right, so we come down here and we compare the encoder pin A current state to the last state, and if it's different, which means it's transitioned, we then say, okay, well, is it high? And if it is high now, since we know it's different, it's changed. If it's high now and encoder pin B is low, we know that we are going counterclockwise. Where if it's low now, because it just changed, but and then B is high, we're still going counterclockwise. So we know these two conditions mean we're going counterclockwise. If it's not equal to either one of these conditions, then we know we're going clockwise. Now, if encoder pin A didn't change, it's possible that encoder pin B did change. So we're going to go over here and we're going to look, and if encoder pin B has changed, then we do the same comparison. Has it just changed to high, and what is pin A, which is at low, or is it just changed to low and encoder pin A is high? If that's the case, we are going clockwise, and if it's not, then we're going counterclockwise. So let me upload this sketch. And we're going to look at the serial monitor. And you're going to watch me turn it, and every click that you hear, you will see it goes up, just like that. And it goes down just as easy. So it works both directions very quickly, much more accurate than what it was before. So you hear every click that it goes up or down. So that's a rotary encoder. And now I'm going to put a link to the same website of the encoder I'm using. There's many different encoders out there. I have some that have lights in them. I have some that have switches in them. So when you push on them, they turn a switch on. This is the one I have here is a very basic 3-pin encoder, and it just has a common pin, and it has an A and a B pin. So if you come down here and look at the diagram, We get past all their stuff. Here somewhere. I don't see where it gives me the actual pins, but basically there's 3 pins, and it's there it is, A, C, and B. So C being common, and then channel A and channel B. So that is what I'm reading. This, in my case, channel A goes to pin 2, and channel B goes to pin number 3. So it's very simple after you think about it. It takes, and you know what? It took me a little while to write the code because I had to read through this. I had to go right to left. So if I'm turning it clockwise, I had to say, okay, when A goes high, I know I'm going clockwise if B is low. And I had to walk through the logic in here to figure it out. And actually, here's a great example right here. Is this little D is like an indent. So you can see every time it clicks, and you go right or from left to right. And then you go right to left, and you can write the logic around it. But I'll have the source code out there, and you can see the logic. And they all the ones I have seem to work very similar to, if not exactly the same. They just have different features. Like I said, some of them I have are lighted. I have one that's RGB, so there's pins for the RGB LED, and there's switches on some. So they're all very, very similar. All right, I think that is it for the week. So let's see, get back here. Where'd Bob go? Oh, there you are. I forget where you are. I moved you to the other Skype.
I'm still here.
Yeah, let me get your volume a little bit higher. So did you get to watch any of the stuff with John?
No, I didn't. I got in, and first thing I did was get into the live chat and ask if you wanted me to join.
Yep, sorry.
So,
how long were you waiting for? I saw that. I had it kind of hidden on my screen, so
2 minutes, if that,
Okay.
which was fine because I needed time to get the lights set up and get the camera on.
Gotcha. So yeah, actually, he did a great job on the I2C stuff, and he definitely a good resource. I'm actually using the control source that I designed tonight, so I'm switching with it. So you see me bouncing around trying to find out where things are because they're not all labeled yet.
Ah, okay.
But I'm actually using it, so it's functioning good.
Okay.
So
well,
it's all I2C based.
That's good. And just unfortunately, I was running late tonight.
Nope, that happens.
I had a conflict, so.
That happens. I was going to call you afterwards or send you an email afterwards to make sure things okay, because I know you were been in the process of moving or something recently, so I didn't want.
Well, tonight I was at a Crime Watch meeting, and I was committed to that. And
you weren't committed, right? Committed.
No, I was not committed.
Okay. Just
I
checking.
was committed to go and say something. So
yeah.
I didn't realize until about 4 o'clock this afternoon that I had a conflict with the show tonight. It just the right side of my brain and my left side were not communicating
That's
today,
okay.
unfortunately. So
I didn't say much tonight either. I mean, John did most of the work, so.
well, it's unfortunate I was late because I had a couple questions for him. So
Oh, we can still ask him. He'll probably watch the show back. You can probably ask him right now. He'll answer you back.
okay. Well, I was your email that you sent earlier. The questions that I wrote down were how does he handle multiple slaves if they end up with the same address?
Oh, he explained that.
Oh, he did explain that. Okay,
Yeah.
then I'll be watching the show. How do you handle slow acknowledgments?
He explained that one too. There is no such thing as a slow acknowledgement. If you don't answer within 35 milliseconds, your answer isn't coming back. It assumes you aren't there.
All right. Well, that's good. All right. So
I kind of asked that same question. So.
You asked the same question. And then I wondered, would there ever be a time that you would have multiple masters? And would you ever want to do that? I mean,
he said yes, but he said it was complicated.
Okay.
He didn't go into detail about that.
Okay. Well, I kind of wondered if it was even possible, and in what circumstance would it be useful. And then the more than probably the most practical of the questions that I had were, what kind of wire lengths can you have between devices?
So I asked,
I've never done anything more than a few inches.
I've asked that same question. He said that in his lab, he's done like 2 to 3 feet, and then he starts having problems.
Okay. So relatively short wire length, but in the kinds of things we'd be doing, you wouldn't have feet worth of.
Yeah, well, actually,
distance.
the thing that I'm doing with this control surface, I'm concerned because I'm running basically one I2C bus, which has 8 pins in it. So it has power and a bunch of other things, and I'm running it from board to board to board to board to board. So that's kind of why I was asking the question. So if I get any kind of size to it, I could get a good length out of it. So I have to consider all that stuff.
Okay. Well, so I'll have to go back and watch the show later, because those were the first questions that I thought of.
We talked about I can't remember what the device is called, but it's like a multiplexer, or it goes in between I2C buses, so you can put different voltages in there. So I'm going to look at that and see if that's how I would do longer lengths and stuff. That's kind of how he described it, is different voltages, disparate voltages, and longer runs because of the capacitance. You put these device in there. It's actually in the thing I sent you. He talks about it in there as well.
Okay. Well, then I will definitely be watching the show.
Yeah, but I'm sure he'll answer back questions.
Okay. Well, good.
So how are things going with you down there?
It's very busy, but going good.
Yeah, well, busy's always good, right?
Yeah, busy's always good. I did get we've had a couple people email about rainbow Duinos.
Yes.
And I got mine in. I think I got it in Thursday last week, and didn't open the box from Amazon until Sunday. And I have successfully gotten one red LED to blink.
That's a start.
That's it. So
just takes one.
So I know I've got a working unit. I just don't have it doing anything interesting yet. So I'm fighting the connections right now. So I'm not quite sure what I'm doing wrong, but I'm working on it. So, but I have it.
So before I went to California last week, I emailed you and said about well, I think I talked about this on the last show too, about making an Arduino Ethernet shield. So yes. I started that. Basically, it's a lot bigger. It does a lot more than just Ethernet. It does all the other connections that I need for this control surface. So I mean, rather than like stack a bunch of things on top of it, I decided to make it. So I'm almost done with that. I've been working on it little by little. I'm in the layout stage now with the actual board. So hopefully soon I have something. I'm going to send it to you and then have you take a look at it for me and make sure I'm not going crazy with anything.
Okay, sounds good. Well, here is the here's the Netduino with a RGB on it. So I do have it.
Oh, very cool.
So now I'm just fighting to get it to work, to do something at this point besides blink one red LED.
Right. And it just uses regular programming out of the Arduino, right?
I've gotten conflicting information. I should be able to drive it with Arduino, but it also looks like I can upload a sketch directly to it.
That's what I thought. I thought it was an actual Arduino chip designed just for this.
But I don't have that. I don't have it working, and I don't have it debugged yet.
Gotcha.
So that's where I'm at now.
That sounds like fun.
Yeah, it's right now it'll be fun later. Right now it's a headache. So.
All right. Well, I'm glad you could join finally tonight. I was getting a little worried about you.
Well, it just makes me mad that I didn't think about, I got too many calendars that are too disconnected right now.
Gotcha.
But I got a plan, and I'm implementing the plan now. So. Okay.
All right. Well, I think that's all we have for tonight. Just a few reminders before we go. You can watch all of our shows at youtube.com/TechZenTV. And if you're a Twitter person, we are at TechZenTV. And if you're talking about this show, Let's Make It, make sure you use the #, Let's Make It. So we have a hashtag Let's Make It. And I am monitoring that. I have a search set up so I do see anything that you tweet. If you're on Facebook, which just about everybody is, go to facebook.com/TechZenTV and click the button there. It says like. And we will definitely appreciate that. All of our show notes are at TechZenTV, or you can go to letsmakeit.tv as well to see those show notes. And this show is recorded live every Monday night at 9 p.m. Eastern. And we were off last week because it was a U.S. holiday, but we're back this week and we're back next week. And next week, I'm actually going to take what we did tonight with the encoder and I'm going to connect it to a stepper motor and a DC motor. So we're actually going to be able to turn the motor by turning the encoder. So that's next week's project.
And then hopefully I'll have the Rainbow Arduino working and we can go through that.
Very cool. That would be great. All right. Well, thanks everybody, and we'll see you all next Monday at 9 p.m.
Good night.
Night. For show notes for this show, contacts, and more, go to the TechZen.tv website where you can get show notes for all of our shows. We love to hear from our viewers and listeners. We have an email, a Twitter, and a phone number where you can contact us for each show. For details, visit the TechZen.tv website and get the show details. You can also make a video and upload it somewhere like YouTube or Vimeo, and then just send us a link. You never know, you may see your video in a future show. You can get all of our shows delivered automatically to your favorite device by going to your favorite podcast website like iTunes and subscribing. Each of our shows also has a YouTube channel you can subscribe to get regular updates. Our shows are also available on most internet radio networks like Stitcher and TuneIn Radio. You can also watch and listen to our shows on Xbox, TiVo, and Roku. You can even find us on your Zune.